In this session, we are going to learn about the concepts of stiffness and strain energy when a member is subjected to different types of loading like tension, bending, and torsion. And these concepts are strictly restricted to well within the elastic limit in the stress strain curve. Stiffness is the ability of a member to resist deformation under the action of external load. Obviously, when we say the element is stiffest, it means that it will deform the least. And modulus of elasticity is the parameter that will quantify the stiffness. There are situations in the design field where we have to use stiffness as the design consideration to prevent the excessive deformation. So we specify the limit of deflection within the elastic limit. For example, let us take the case of a shaft supporting one or more gears. If it is allowed to deflect more than the specified limit, it will affect the meshing of the gear teeth. In the sense, there will be uneven load distribution over the face of the gear, which may lead to failure. Not only that, it will result in the misalignment between the axis of the shaft and the bearing. Bearings will support the shaft. So this will lead to the uneven wear of the bearing surfaces. So in these situations, we use stiffness as a design criterion. And we will study this elaborately in Unit 2. So the resistance to deformation, the expression will change for different types of loadings. For the case of axial loading, it is actually the force required to produce unit deflection. That is, K is equal to P by delta. If a member is subjected to axial loading, be it tension or compression, we know that from mechanics of solids, deflection is PL by AE. You recast this equation as P by delta because we need K, which is AE by L. So K is equal to AE by L is the expression for stiffness in axial loading. Similarly, for the case of torsional loading, it is the amount of twisting moment needed to produce unit angle of deflection. That is K suffix T. T indicates torsional loading. Mt by theta. And from the torsional equation, we know that theta is equal to MTL by Jg, where Mt is the twisting moment, L is the length of the shaft, J is the polar moment of inertia, and G is the shear modulus or rigidity modulus. Now you recast this equation as Mt by theta to get Kt, that is Gj by L. Stiffness in bending. Unlike in axial loading and torsional loading, where the stiffness equation was fixed, whereas in bending, the expression for stiffness changes depending on the end conditions and the type of loading to which the beam is subjected to. Because we had learned from the chapter of deflection of beams there that we had a table of deflection equations, right? For the case of cantilever beam, the lateral deflection is PL cube by 3EI, where E is Young's modulus and I is the moment of inertia. So recast this as P by delta, you will get the stiffness 3EI by L cube. For the case of simply supported beam subjected to center load P, so this is very, very important. Whenever you write the expression for stiffness in bending, you have to specify the end conditions and as well as the loading condition. It is delta is equal to PL cube by 48 EI. P by delta will be equal to 48 EI by L cube. So these deflection equations can be easily obtained from data table, and you can rearrange the terms to get stiffness. The concept that we use in the elastic region is the strain energy. What is the strain energy? So you apply a load, the material deforms, and within the elastic limit, what will happen? If you remove the load, all the work input will be recovered, right? So, and this input work will be stored in the form of potential energy or strain energy within the component. So when you remove the load, all the input work will be converted into output work without any loss. right? The strain energy will be completely given up. The material behaves like a perfect spring. So thus, potential energy is simply a measure of work done by the external force, right? With no loss of energy in the form of light, heat, or sound. So if you want to quantify strain energy, just measure the work done by the external force within the elastic region. So far, we looked at materials subjected to linear elastic behavior. So there are materials like rubber and other polymers which will have non-linear elastic behavior also. So how to evaluate the strain energy in the case of a rod subjected to axial load here? A rod subjected to axial load P and it undergoes a deformation of X. So now clearly work done by P is equal to strain energy. We take a small uh, portion of the deformation dx and calculate the elementary work, that is P dx. And this is clearly equal to the area of uh, width under the load deformation diagram. So here you have a non-linear elastic region. Okay, so so the total work done by the force will be equal to simply integrate from 0 to x1. X1 is the total deformation undergone by the specimen, which is seen in this px diagram. So total work is equal to total strain energy. Suppose if the uh, elastic deformation is linear in behavior, we know the function, which is simply P is equal to Kx. Substitute for P in the above equation, write Kx dx, integrate it, you will get half Kx1 square, or in general we say strain energy is equal to half Kx square, or in terms of load it is simply half of Px in general. Okay, so you must remember this for the case of linear elastic deformation. If it is non-linear, you have to find the function for P in terms of X and then integrate it to get the total strain energy. To avoid the effects of size, what we do is we always express the strain energy in terms of per unit volume. So divided by V, right? Because see, uh, you might take a component with different size and shape, though it is prismatic, having regular geometry. I can choose a different cross section. So strain energy, right? To no kind of normalize, uh, we normalize with respect to volume. So U by V, divide it, U by V, and even on the right side you will get A by L. So I'm dividing by V on either sides, so it doesn't affect. So lowercase u represents our strain energy density. Lowercase u is equal to U by capital V, where V is the volume. Strain energy density. P by A is sigma. Suffix x indicates the loading is along the positive x direction. Dx by L is simply what? Incremental strain, that is d epsilon x. Okay. So the total strain energy resulting from the deformation is equal to area under the curve until epsilon 1. Now if you remove the applied load, in some cases, suppose if the material is has entered plastic region, you can recover only the work, elastic work. Okay, the triangle shown in the orange color in this figure can only be recovered. So there will be some permanent deformation left in the component with a strain epsilon P. Okay, that cannot be recovered, that will be dissipated as heat. Okay, so the strain energy density of a member subjected to axial loading is equal to integral from 0 to epsilon 1 sigma x d epsilon x is the general expression which you must remember. Now if the member is having non-linear cross section resulting in non-uniform stress distribution, how do you derive the total strain energy? So let us invoke our total strain energy density equation. U is equals to du by dv. So what do we need? U, right? You integrate it, u dv. So as long as your u is less than ui, that is below the proportional limit, right? We know this sigma x square by 2e. You can recast the previous expression sigma x by sigma x dx, right? You invoke your Hooke's law, right? You invoke your Hooke's law and substitute it, you will get sigma x square by 2e. Because let us assume now in this case linear elastic behavior, and then I can use Hooke's law and rewrite u is equal to sigma x square by 2e into dv. So that is what under uniaxial loading we know what is sigma x p by a dv is equal to a dx. If you take a small element, recast it and change the limits accordingly now, because I'm changing the limit from dv to dx, so integral will change from 0 to L. So this is the expression for strain energy in general, 0 to L p square by 2ae dx. Okay, so for any portion of your element, you can calculate the total strain subjected to axial loading. So please remember this general expression, 0 to L p square by 2ae into dx. For rod of uniform cross section, it is simple, right? So p square L by 2ae, that's it, because length your diameter is constant, so, right? Now let us see the expression for strain energy for the case of a beam subjected to bending load. So here we have a beam subjected to UDL, and then we have replaced with an equivalent load. Let us start with our general expression. U is equal to sigma x square by 2e into dv. Okay. Now, what is the stress in case of bending? You have to go back to bending equation. So sigma x is simply my by I, right? So whole square. That is what we have substituted here. So again dv is equal to dA dx. So change the limits of the integral. So 0 to L and integrate over the area, entire area. Recast this. Take out the integral over the area y square dA separately. That is actually moment of inertia I. So one term I in the numerator and I square in the denominator, which will cancel out. So we'll get 0 to L m square 2ei by dx. For an end loaded cantilever beam, right? We know so this is the general expression for strain energy in bending. U is equal to 0 to L m square by 2ei. And m will change for different end conditions and loading conditions, and accordingly you have to pick up m, evaluate m, and then substitute here to get the expression for strain energy. So here m is simply minus p by x, because negative sign, it is creating hogging moment. Substitute here, so you will get p square L cube by 6ei. So in this fashion you can derive the strain energy for bending depending on the loading and end condition. But if you remember this general expression 0 to L m square by 2i dx, that is good enough. For any beam you can evaluate the total strain energy. Now for the case of torsional load, it is again tau square xy by 2g into dv. So what is the expression for shear stress? It is t square rho by t square rho by j, right? T rho by j whole square, where rho is the radius here. So in your mechanics of solids you would have used r, so don't get confused. Again replace dv, change the limits of the integral, and here take out r square dA. You would have seen r square dA. Here we are using rho square dA. What is integral of rho square dA over the entire area A? It is simply polar moment of inertia, that is j. So jj will get cancelled. You will get 0 to L t square by 2gj. This is the general expression for strain energy. So for the case of a simple rod subjected to twisting moment t in t prime, you can substitute to get t square L by 2gj. So this is the way we derive expression for strain energy. So please remember the expression for strain energy we may be using. There are situations where we might get axial loading. See, in all these cases, the loading It was assumed, or it was actually given in the problem, that line of action of the applied force will pass through the centroid of the cross section. What if it is not so? So here is an example. So I've shown the top view as well as the side view. So here we have a P which is not acting at the geometric center of the member, slightly offset by a distance E, which we call it as eccentricity. Okay. So now from the principles of statics, you can replace it with a moment, right? Couple moment, isn't it? P acting along the axis of the member with a couple moment P into E, right? When you have a moment, obviously you will have a normal stress distribution as shown in the figure. This we had seen. This is the stress distribution in bending. In this case, for the load acting along the axial direction, we have a uniform stress distribution. You superpose these two because we are well within the elastic region. I can apply the principle of superposition. What will happen to the stress distribution? You just see it, right? The addition of tensile force, isn't it? I'm replacing this eccentric loading with a couple moment and an axial force, and accordingly the stress distribution changes. Now what is the total stress in this case? This is what I said. So the eccentric force P can be replaced by a parallel force P passing through the centroidal axis along with a couple PE. So P produces a uniformly distributed tensile stress of P by A magnitude, and a couple produces bending stress, right? Py by I. You can add these two because these two are scalar quantities and vary linearly within the elastic region. So the net stress plus or minus, depending on the type of P, it can be compressive or tensile. Okay, if it is tensile, you will have plus sign, otherwise minus sign. So in our entire course, we can use principle of superposition. As I said in the beginning of the course, we are not going to deform the component beyond elastic limit. And in the we are done with this session, and we shall look into the problems in the next session. These are the references I've referred to. Thank you.